Alright, so let's now examine what would happen if our gyrator circuit involved using transconductors that had a finite output resistance. So we'll redraw our gyrator circuit, and we'll use the single-ended gyrator circuit representation. So here we're not going to even put a differential input at the input of the gyrator. So the first GM circuit has a value of GM1. We feed back a current using a GM2 device. Of course, our input is here. Now, in our prior version of the gyrator circuit, we had a capacitance only at this node that we called node Y, and we called this node X. Now, a real gyrator circuit has some capacitance due to the input of the gyrator. In other words, there would be some capacitance due to this GM1 on this node. So we'll call this capacitance C2, and it's the parasitic associated with the GM1. And we would also have an output resistance due to the GM2 device. So we can put an output resistance, or we'll label it as a conductance, in this case G2. GM1 would also have some output resistance, or conductance, that we'll call G1. And we'll label the capacitor at that node C1. And this capacitance could be due to an external capacitor that we added, and it could also be due to the input capacitance to GM2, or the parallel combination of both of those. All right, so if we do Kvl and if we do Kcl at both of our nodes, node Y and node X, we can find the following. So we'll start at node Y. Here we have minus GM1, and we'll give both of these transconductors negative transconductance values. So you'd have minus GM1 times Vx plus Vx times, plus Vy times SC1 plus G1 is equal to 0. Now if we look at node X, we'd have minus GM2 times Vy plus Vx times SC2 plus G2 is equal to 0. Oh, and I forgot, we need to put our input voltage source in here, Vx, and we're measuring the current Ix that flows from that device. So here we need to add a minus Ix. Alright, so solving these equations simultaneously and solving for the input admittance, Y sub I, which is equal to Ix over Vx, we would find that the value is equal to G2 plus SC2 plus 1 divided by SC1 over GM1 GM2 plus G1 over GM1 GM2. Now we could make an equivalent circuit here that looks as follows. We would have a resistance in parallel with a capacitance. That would represent this G2 term and this C2 term. And finally, we would have this all in parallel with an inductance in series with a resistance. Now this is the single-ended representation of the circuit, so all these passive components would go to ground, and this would represent the input of our circuit. So we have this resistance that we'll call Rp, we'd have a capacitance labeled Cp, and we'd have an inductance labeled L, and a resistance labeled R sub S. Now R sub P is equal to 1 over G2. C sub P would be equal to C2. L would be equal to C1 divided by GM1, GM2. And RS would be equal to G1 over GM1, GM2. Now what we can see is that if our circuit were ideal, in other words, if the conductances associated with the GM devices were to approach 0, these resistances would approach infinity. The parallel resistance would approach infinity. In other words, this resistor would go away. The RS would approach 0, and this would go away. And we would be left with a parallel resonant circuit consisting of L and CP. Now, looking at this circuit, we see that it's got some kind of parallel resonance mode. So this looks like a resonator that we looked at the other day. So let's examine the properties of this resonant circuit. So here is our input voltage. We have RP, CP, L, and RS. And we know that both RP and CP are due to G2 and C2. And we know that RS and L are due to G1 and C1. If we were looking at this circuit as a resonant circuit, we would find that this would be equal to omega naught, which is equal to 1 over the square root of 1 over L times CP. And if we substitute the values for L and CP into this equation, we would see that it would be equal to GM1 times GM2 divided by C1 times C2. Now, oftentimes we define a term for our transconductors called the transition frequency, omega t. And we can show that the transition frequency of a transistor is where the current gain, I out over I in, versus omega is equal to 1. So let's look quickly at a transistor circuit where we'll neglect the CGD for the circuit and only look at CGS. So here we have our input voltage and we have an output current. So we could say that I out is equal to GM times Vn, and we know that Vn is equal to In times 1 over S times CGS. Substituting for Vn into this expression, we could get I out over In is equal to Gm divided by S times CGS. And we're looking for the frequency where this expression goes to 1. So we could say that S is equal to Gm over CGS, or we can say that the transition frequency is equal to Gm over CGS. This is the frequency where the current gain of the device goes to unity. Looking at this, we see that we have a Gm over a CGS, which is very similar to having a big Gm over a big C1. So we could say that our resonant frequency of our gyrator circuit would be equal to the transition frequency of both of the individual gyrator circuits. In other words, Gm1 over C1 would be omega T1, and Gm2 over C2 would be omega T2. Alright, so what we see is that our lossy gyrator circuit looks like a lossy RLC circuit. In other words, it has some resonant frequency and some quality factor. So it acts like a bandpass or a band stop circuit.